Good morning, class. We'll now discuss section 6.2, the standard normal distribution. So recall from last class that we ended stating that the probability of a continuous random variable is equivalent to the area under the curve of the density function. Now, it turns out that a normal curve is completely defined by its mean and standard deviation. Theoretically, we could go on drawing normal curves forever, since there are infinitely many of them. The mathematical function for a normal distribution only requires the values of the mean, mu, and the standard deviation, sigma. And if you're interested, it's given as follows. F of x is this exponential function. Notice it's an e to the x type function. Now, we won't discuss this function any further, but you can use a graphing calculator and mess around with different values of mu and sigma and see what the normal distributions look like. Here are a few normal curves with means -4 shown in blue, -2 shown in purple, 0 shown in red, and 1.75 shown in green. The standard deviation determines the shape of the bell. A smaller standard deviation creates a tall, more narrow bell shape, whereas a larger standard deviation creates a short, more flat bell shape. So can you guess which curve has the smallest and largest standard deviations? That's right. We would guess that the curve shown in purple, centered at -2, has the larger standard deviation since it's more flat and spread. And we would guess that the normal curve shown in red, centered at 0, has the smaller standard deviation since it's more narrow and tall. As we stated in section 6.1, the area under the normal curve is what we are most interested in, as it is equal to the probability of a random variable falling within that region. To calculate the area under the curve, we must apply integral calculus, but this is a technique beyond the scope of this course. To avoid repeated calculations, mathematicians developed a way to standardize normal curves using standard scores. So remember from chapter 3, section 3.3, we talked about standard scores, or what we called z-scores. The resulting distribution is called the standard normal distribution. This is a single curve used for reference that has greatly simplified inferential statistics. Recall that a standard score, or z-score, is a number which indicates how many standard deviations a data point is from the mean, and it's given by the following formula. Z equals x minus mu over sigma. Remember, this is just our data value minus our mean divided by our standard deviation. The standard normal distribution is a normal distribution with a mean equal to 0 and a standard deviation equal to 1. Such that the following properties are true. So 1, it is bell-shaped and symmetric about its mean. 2, it is completely defined by its mean, mu equals 0, and standard deviation, sigma equals 1. 3, the total area under the curve equals 1. And finally 4, the x-axis is a horizontal asymptote. This just tells us that the curve gets closer and closer to our number line that we draw, however, never passes through that number line. Using our mathematical function with mu equals 0 and sigma equals 1, we get the following bell-shaped curve. So here's our standard normal curve. Notice it's centered at 0, and our standard deviation is 1. Notice that the x-axis is our horizontal asymptote. So the curve gets closer and closer to it, but it never actually touches or crosses through that axis. Let's look at an example. Consider a normal distribution with mu equals 48 and sigma equals 5. Convert an x value of 45 to a z value. We find the z-score as follows. Remember that z is given by x minus mu over sigma. So our x is given in the problem, an x value of 45. Our mu is 48 and our sigma is 5. Calculating this using our calculator, we get z equals negative 0.6. Consider, now we're looking at the same normal distribution with mu equals 48 and sigma equals 5. Draw two normal curves, one indicating the placement of the x value in relation to the mean and standard deviation, and the other indicating the placement of the z value on the standard normal distribution. We will not worry about the particular bell shape of each distribution, and we'll draw each identical just for convenience. Now again, sigma equals 5 is larger than sigma equals 1, which is our standard deviation for our standard normal distribution. However, we'll just draw them as a traditional bell-shaped curve for convenience of our picture. We will, however, emphasize that 1 represents our x distribution, showing our values x equals 45, mu equals 48, and sigma equals 5, and the other represents our standard normal distribution, showing our values z equals negative 0.6, mu equals 0, and sigma equals 1. Since each value is within one standard deviation, we will only label the mean along with the values one standard deviation away from the mean. Remember that a negative z-score falls to the left of the center on the standard normal curve. So here is our x distribution. Notice that I've drawn my bell-shaped curve with my horizontal axis. My horizontal axis contains all my data values. So 48 is going to align with the highest point of my bell shape. Now I'm going to use my sigma equals 5 to go one standard deviation to the right and one standard deviation to the left. And notice that 45 falls a little between the mean and one standard deviation to the left. Now, a similar picture, again, I'm going to draw my bell shape just for convenience, exactly the same. And now this axis is going to represent my z values. So since the mean is 0, 0 is going to align with the highest point, and my sigma equals 1, I'm going to go one standard deviation to the right and left, and notice negative 0.6 again falls somewhere between the mean and one standard deviation to the left. Around the 19th century, tables were created so that the calculus needed to calculate the area under the standard normal curve did not have to be repeated. All that one needed to do was read the tables in order to find the desired area under a normal distribution. For our class, we will use the cumulative normal distribution tables. These are our statistical tables A and B found in our Canvas course, which give the area under the standard normal curve to the left of the given z value. And we're going to emphasize that when we start using these tables. So our tables always give the area to the left. Here's an excerpt of Table B. Notice that the z values given in the table are rounded to 2 decimal places. This will be our rounding rule for all z values calculated in our course. The first decimal is listed in the left column. Notice that I have my z column and I have 1 decimal value. The second decimal is listed along the top row. Where the appropriate row and column intersect, we find the amount of area under the standard normal curve to the left of that particular z value. The picture above highlights the fact that the area to the left of z equals 1.37 is 0.9147. Notice that if I take my 1.3, the first decimal place of my z value, and then I look at my second decimal place, 0.07 and I align these, I get the area to the left of that value. We will now discuss how we find areas using our tables A and B. Using the cumulative normal distribution tables to find areas under the standard normal curve, we will start with area to the left. To find the area to the left of Z, we simply look up Z in the appropriate table. If Z is negative, we use table A, and if Z is positive, we use table B. Let's look at an example. Find the area under the standard normal curve to the left of Z equals 1.37. Since our Z-score is positive, we know that it falls to the right of the mean. Remember that mu equals 0, as shown below. So here's our generic bell-shaped curve. Our highest point aligns with the mean, 0, and 1.37 on the number line is to the right of 0. Therefore, we expect that the area under the curve to the left of this value will be greater than half of the total area. Remember that this gives us 0.5. Now, to read the table, we must break the Z-score into two parts, one containing the first decimal, 1.3, and the other containing the second decimal, 0.07. Notice that 1.3 plus 0.07 gives us our Z-score 1.37. A look across the row labeled 1.3, so we find 1.3, and down the column labeled 0.07, in table B, since it's positive, gives us an area of 0.9147, as shown below. Now let's ask ourselves, how do we find area to the right, since our tables only give us area to the left? To find the area to the right of Z, we again look up Z in the appropriate table, but now we use the complement formula and take 1 minus the value found in the table. And this is because area to the right is the complement of area to the left. Let's look at an example. Find the area under the standard normal curve to the right of Z equals negative 0.90. Again, we need to use our appropriate table. In this case, we'll use table A to first find the area to the left of Z equals negative 0.90. We do this by breaking our Z-score into two parts, negative 0.9 and 0.00. And this is because when we add the two, we get our Z value. A look across the row labeled negative 0.9 and down the column labeled 0.00 in table A gives us an area of 0.1841. Now pause the video and take a look at your table A and make sure that you get this same value. However, we are not done. We must remember that area to the right is the complement of area to the left. So we must take 1 minus the value we just found in our table. Using this fact, we see that the area to the right of Z equals negative 0.90 is 0.8159, as we can see below. Notice that our table gave us this value, and we've used our complement rule from chapter 4 to obtain this value. Finally, area between. To find the area between two values, we'll label them Z1 and Z2. We look up both values, Z1 and Z2, in their appropriate table. Then we take the larger value in the table minus the smaller value in the table. Let's again look at an example. Find the area under the standard normal curve between Z1, which is negative 1.68, and Z2, which is 2.00. In this case, we break each Z-score into two pieces, negative 1.6 and 0.08 for negative 1.68, and 2.0 and 0.00 for 2.00. And look up each value in our table A and table B respectively. Notice that Z1 is negative, so it's going to be found in table A, and Z2 is positive, so it's going to be found in table B. We get the following areas, 0.0465 and 0.9772. Again, pause the video and make sure you're getting these values as you're following along. To find the appropriate area, we take the larger value minus the smaller value. This gives us the following, 0.9307, as shown below. So we take our larger area minus our smaller area to get our area between. There is a way to use our calculator, however, we will not introduce this technique until the next section.